literally like, I don't know, like this stuff. That's
Space.
this stuff is like.
It's working. All right.
This is bad.
Alrighty. Well, one of the students from the previous class actually donated, the rechargeable batteries, so that's why we can still be using the cordless mic in this classroom. Here we go. There we go. All right, so I think it's good. Yep. So I think in the future, community colleges will be crowd-funded. So with every single homework assignment at the bottom, there's a donate button. Or you have to uncheck the donate button every single time when you're turning your homework. Otherwise, we'll sneak in some donation right there. Anyhow, so this is your homework assignment, ATOF. I do want to go through the homework assignment, but in a way that I'm hoping it will be helpful, not only to understand the floating point representation, but also how to structure your program. I know all of you have taken CISP 360, okay, before this class. Some of you might have taken other programming classes as well. Okay, so I want to do this whole program today interactively, and just go through the whole process that you guys had to go through for the past 2 weeks or so, right? And I can tell you, I have not written this program before. I just knew that program is possible. I did not actually write it. So this is my first time writing this program as well. So I will goof up a few times, okay? I will goof up a few times. If not for anything else, I do want to show you guys how to debug a program. Okay, because I learned that that is one thing that some professors do not teach, is how do you debug a program. They will teach you, okay, this is a function, this is a parameter, this is a pointer, this is a structure. They will test you on your knowledge, right? But they don't teach you what to do when your program does not work. And how often does that happen? Well, it happens to me too, okay? So nobody can actually write programs that are bugless, okay? So the key is, how do you look at a program that is not working and make it work? But I'll make that the second question. The first question is, how do you write a program in a way that lends itself, the process itself, to easier debugging? The first approach is, I'm going to write the entire program, like 400 lines or something like that, which is actually considered a pretty small project in a commercial scale, and now debug all 400 lines of code all at once. Probably not a good idea, right? So the best way to write a program is really to write it piecemeal, and then have test cases to test it along the way, and you just say, okay, I'm going to write 16 lines, okay, about there, lines of code, and then you test the program. Does it work at least up to this point? If it does not work up to that point, don't even proceed. Don't even go any further, because it's not going to be helpful. Okay, so the key is only write a small number of lines each time. So when the program does not work, it probably has to do with those few lines of code. Now there are cases where bugs are hidden, or masked, so that you do not discover the bugs early on, and then later line of code actually triggers an earlier bug to show itself. That's possible too. But we want to write the program so that it doesn't fall into that particular problem. So I'm going to write the program interactively here, and I just want to make sure that everybody can read the screen, including people all the way to the back. Is that okay? Can everybody read? Okay, so the font is big enough? Okay. All right. So I personally like to use structures because it really helps to bundle everything together. So this way, if I need to break up the code into smaller subroutines, there's only one pointer to pass. I don't need to pass like 20 gazillion, individual parameters, which is a problem because when you have to pass multiple parameters around and they all have the same type, which in this case, there are a lot of uint64s, right? So if you pass it in the wrong order, the compiler cannot help you if you pass those things in the wrong order, or if you pass the same thing twice, okay? But when you use a structure to do it, at least it eliminates the possibility of passing the parameters incorrectly. Another question, can you pass an int, a regular int int, as a uint64_t? In other words, you use a regular int and pass it to a parameter that is expecting a uint64t. The answer is yes, because it is a typecasting that is automatic, it's coercion, okay? So the compiler won't give you a bug, won't give you a warning in that case. The only time that may not happen, I'm just saying may not, is when you pass by reference. So when you pass by reference and your parameter is an int variable, but the parameter is expecting a by reference uint64 parameter, that may not, that may generate a warning or an error. Okay, but since we're using C and C++, regular C, I only use regular C in this case, so that may not give you any warning at all because there's no such thing as passing by reference. You have to cast something to a pointer to pass it. Okay, so we'll go ahead and just do this part here. So we'll say, and I'm going to generalize this to ATOF as a structure because it's not just the parsing part, but also including the conversion part. So I'm going to do it like this, ATOF struct, and in it we'll remember the sign bit. So we'll remember the mantissa. So mantissa needs to be int64_t because we definitely want to use 64 bits to remember the mantissa. And I want to use M10 to remember that this is a base 10 mantissa. And then uint64_t, E10 for the base 10 exponent. And then we'll have, oh, that one cannot be uint because it can go negative, so it has to be signed. If you're worried that int may not have enough range, you can always just say int32_t. That will give you definitely enough space for the exponent in base 10. Same thing for the exponent in base 2, E2, like that. And then we know that we have a few other things. We can always add to it later on. Okay, so we'll just keep it like this. And then for parsing purposes, we have const char p. P is a pointer to the original string. So we have, well, we'll start with this much. Okay, we can always extend this later. All right. So the first thing we need to do is to parse the input. And as I said in class, I will break it up into 3 main parts. The first part is to parse the sign of the number in general. The second part to parse the mantissa. And then the third part to parse the optional exponent. Okay? So let's go ahead and see how we'll do that. And I already know that I'll need some helper functions just from experience. Okay, so this way I'll just go ahead and define isDigit. Okay, there is a function called isDigit, by the way, with a lowercase d. You can call that if you want to. But I'm just going to write it myself, okay? There's no harm in doing this myself because isDigit is really just checking whether CH in this case is between the ASCII code of 0 and the ASCII code of 9 inclusively. So it's relatively easy to specify that. So I need CH to be at least a 0, and I also need to make sure it is no more than a 9 in terms of ASCII code. And that's all. That's all I need to do to check whether something is a digit or not. All right, so the first thing I need to do is to check the sign and make sure that the sign is read correctly. So we'll go ahead and call a subroutine to do that. Okay, parse sign. And before we do that, we have to create an instance of the structure. Because the program does not really need to pass ATOF struct around, you can just use a local variable for this purpose. There's no need to do a malloc or new, like in a data structure class. So I go, say struct ATOF struct, and give it a name. I'll just call it A.
Question?
Yep.
Shouldn't it return be a bool or this digit?
Say that one more time.
This digit shouldn't we return a boolean?
Oh, in regular C, there are no booleans.
Oh, yes, right.
Yeah, I'm using like plain C. Now, why would I encourage anyone to program in plain C instead of C++? I mean, C++ has to be better, right? Because of the plus plus. But why would I? Yeah.
Because C is an older language, so we'll see it more often because people have already coded it and we'll have to update their code.
That is part of the answer. That's definitely one driving force, why C++ is almost entirely maximum compatible with C. Everything you can do in C, you can do it in C++. Pointers, okay, dereferencing, treating a pointer as if it is an array, all of those things you can do, all the bad things, okay, you can do in C++ as well. But why do you think that is the case? Java makes a pretty clean cut from C. But why do you think C++ did not make a clean break from regular C? Yep.
Isn't like the library in C++ pretty much just an extension of C?
You can always rewrite the library. I mean, that's not that big of a deal.
I mean, just like the idea behind C, because of object oriented.
Okay, so we kind of have to trace back to the history of C. So this is going to be a long class. We have to trace back to the history of C. Why do you think C was invented in the first place? What was the motivation to write C? Or the programming language C? Right? Yeah.
More readable code.
More readable code. Who came up with that? Who came up with the original C programming language? Dennis Ritchie, and he has a partner. You can look it up. But Dennis Ritchie is one of those people, okay? One of those two. And why do you think he wrote the C programming language? Why did he invent the C programming language? What was he doing at the time? What was his major contribution other than the C programming language?
Did you break up with his girlfriend and try to invent something that is very crazy?
That would be George Lucas. Okay, so we want to look at C. Ritchie. What was his last name again? No, that's his last name. Dennis. There we go. I'm pretty sure I misspelled something here, but it's close enough that we can find him. Okay, so let's go ahead and go to the Wikipedia page. And we'll also go to the Wikipedia page of Steve Jobs. Okay, so there we go. Cannot be more different, okay? Look at this guy, and look at this guy, okay? Side by side, okay, so you look, and then look at the time when they passed away, October 5th and October 12th. They're off by only 1 week. Did you guys even remember that somebody mentioned Dennis Ritchie passed away? Like a week after Steve Jobs? Nobody. But trust me, he's not just as important as Steve Jobs, he's more important than Steve Jobs in many ways. So when you look up his contribution, he created the C programming language, okay? Well, that's kind of cool. But he also wrote the original Unix operating system. And guess what iOS really is?
Yeah, Unix.
It's a dressed up Unix system with a nice GUI, okay? So the front end is kind of all Apple, but the back end is all Unix.
Yeah.
So without Ritchie, there would not be iOS. And without iOS, without Unix, there won't be iOS, and there won't be Mac OS 10 either. So Apple will still be stuck with OS 9 at this point. Okay, you guys are way too young to remember what is OS 9. It's not OS X, by the way. The X is Roman 10. It's actually OS 10, okay? So before OS 10 is OS 9, and OS 9 is an entirely proprietary operating system. And why do you think it's a good move on Apple's part to move from an entirely proprietary operating system to a Unix-based operating system? Yep.
Money.
Why do you think it's money?
Well, it's cheaper to not have to license out proprietary code every time.
Absolutely, because the particular version of Unix that iOS relies on is called BSD, which stands for Berkeley Standard Distribution. So it's it's not exactly open source, but it is open, which means the licensing allows Apple to pretty much freely use the base code of BSD. So that takes care of all the kernel and the file system, all the back-end stuff of the operating system. Apple can focus on just the front-end, the user interface. Okay? And that's a lot better than having to maintain the entire operating system. If you think about an operating system, it's like an iceberg. This is the water level. What you see is the tip of the iceberg. What you don't see, which is 9/10 of the volume, is the actual operating system. So Apple says, well, we're going to use Unix here, and we'll write OS X and iOS on top of that. Android is exactly the same way, another iceberg. What we see here is Android. What we don't see is Linux, which is a very similar thing to Unix. I mean, they're not exactly the same, but they are very, very close. Okay? So this really gives you an idea of why Apple went the way of using BSD as their base operating system and only write the GUI part on top of Unix. Okay, so that's kind of the person that Dennis Ritchie was. He was writing the operating system Unix while he invented or created the C programming language. And the reason why he did that was writing code in assembly code, writing programs, an entire operating system in assembly code was not exactly fun. So he created a tool to help himself write code in a more efficient manner. In other words, if you look at Ritchie or Dennis Ritchie as a master carpenter, okay, he was only given a Swiss Army knife to carve out some masterpiece. So before long, the guy said, this is not going to work. I can do it, but I'm really bored with using a little pocket knife to carve out my masterpiece. So he invented his own tool. Okay, he's a circular saw, he's a saw table saw, and all the other tools. And see, the C programming language is one of those things that he invented so that he can write programs in a much more effective way. Is that making any sense? Sort of? Okay? But that is also why the C programming language has all kinds of quote-unquote dangerous features. Pointers, looking at pointers as if it is an array, that sort of thing. Because with low-level programming, that really helps a lot. Okay, you're trying to be efficient, and you're trying to look into the internal representation of everything. And that's why those quote-unquote bad features of C are actually a necessity in the context of writing an operating system. The C programming language was never, ever invented or intended as an instructional programming language. Okay, it's just like a really experienced a master carpenter might have a circular saw that has no safety feature, right? No guard, no interlocking mechanism. You pick it up, you hit the switch, and it goes. Okay, because it was for someone who's really experienced. What happens when you give that circular saw to a high school student in a wood shop class? Fingers will get lost, right? That's exactly what's happening when you use the C programming language as a first programming language, because of all those features, quote-unquote features. Okay, so a little back history, but I think it is actually important that we understand why I encourage people to write programs in plain C, because if you want to get into the back end of operating systems, that is how the back end of an operating system is written in. Okay, all right. So getting back to the program here, after a little story about the history of computer science in a certain way. Okay, back to here. So I want to parse sign first. When I want to parse sign, I'm just calling a subroutine, and I'm passing along a the address of the entire structure. Ampersand A will pass the entire structure. So now we go back and define the subroutine. Parse sign doesn't need to return anything because everything it needs to use is inside the structure that is pointed to by the pointer. So this is a ATOF struct, and the pointer, I'll just call it PTR here. All right, so here is parse sign. Well, parse sign is pretty easy because I only have 3 possible cases, right? I either see the plus sign, which is not really important because the default sign is a 0. I see the negative sign, which means I need to do the negation. I have to remember the sign bit is a 1. Or I see nothing. Well, what do you mean by seeing nothing? Well, I'm not seeing a plus sign nor a negative sign. I'm seeing something else. Okay? Yeah, question?
Yeah, a quick question. So why did you use malloc again?
Why didn't I use malloc?
Yeah.
Because there's no need to use malloc. The lifespan of the ATOF struct does not need to extend beyond the invocation of ATOF. When ATOF is done, I have no use of that structure anymore. So when you have an auto local variable like what we have here, it gets automatically deallocated. But this is also one of the places where you look at a C++ program and you might not even understand how inefficient it might be. Because when you have a C++ program instead of a C program, every time you declare a local variable that is of a certain class, what's going to happen automatically? That is happening behind the scenes.
Memory focus.
Well, the memory allocation part is still on the stack, which is the same as here. But you have to call the constructor. There's always a default constructor for a C++ class. And then when the subroutine ends and you're about to return, what's going to happen? The destructor always gets called. So all of those overheads, they always happen, but you don't see it, right? Because normally you just declare a local variable and then you don't even worry about it at the end of a subroutine. But all of these constructor calls, all the destructive calls, they're all happening every single time you call and return from a subroutine. So this is one reason why I personally, unless I see a value in writing the program in C++, I usually just default into just regular C, so I can see, so I don't miss all those overhead, because I want to make sure that I get to see what the program is actually doing. Okay, so parse sign has a few things to do. The first thing we want to do is to say the default sign bit is a 0. Okay, I can always comment here and just say default sign is 0, which means the number is non-negative. Okay, you can always add that part as well. Okay, so now that we have the sign bit initialized, how many people, well, since I went to the lab and a few people did not seem to understand this particular operator, how many of you did not go through C360 learning how to use that particular operator? Dash greater than ish. Okay. So it means exactly the same thing like this. Okay. So if I want to rewrite this in a slightly different way, it really means the same thing as dereferencing the pointer and then accessing the member S. So these two lines, line 18 and 19 at this point, they are identical. Okay. They're just using different representation, but they're doing exactly the same thing. Is that okay? All right. So by convention, most C programmers would use the first way, but the second way is actually illustrating what it is actually doing. Okay, so at this point I can use a switch statement. Okay, I gave you this code from last week already, so that should not be a big surprise. So the dereference applies to the member P of the structure pointed to PTR. I believe the parentheses are really extra. The inner parentheses are not really needed. I'm gonna have to set, this is shift width to 2, so when it automatically indents, it indents to just the 2 spaces. Okay, so if I see a negative sign, I got something to do because I have to say PTR points to sign is now a 1, okay? Change sign to 1, which means it is negative, and then do a break. And then the other two cases, which is a plus, Okay, there's one more thing I have to do too. The one thing I have to do is to increment the pointer. Every time I see something that I do recognize and I process it, I have to remember to increment the pointer so that I will be ready to process the next thing. Okay, I can do a break here, and then the default case has nothing to do, because the default case is basically just saying, okay, what if it is not a plus and not a minus? What if it's a digit? Well, I'm not supposed to process the digits. Okay, I'm not supposed to process the mantissa. I'll leave it to another subroutine to process it. Is that okay? Okay, all right. If you have any questions at any time, just let me know, okay? So right now I have a program that doesn't seem to do much, but you know what? I can test it. Okay, this program doesn't do a whole lot, but I can still test it because I can put a breakpoint on line 39 and see whether the sign is read correctly with the numbers that we're supposed to process. Yes?
How does A access the constant pointer if the P itself isn't in percent?
Oh, because I forgot to initialize. Good point, good point. So I do have to initialize that, so that A dot P is PTR from ATOF. Thank you, very good. But you just took away, you know, an opportunity for me to show you guys how to debug the program. Okay, so we'll make the program. Now we got main, and then we say GDB main. Okay, we put a breakpoint in ATOF. So if you have used code blocks and you use a click to set up breakpoints and use the watch and stuff like that, GDB is the back end of code blocks. So in other words, behind the scenes of code blocks, this is really what is happening. And you can actually hand enter specific GDB commands in code blocks as well. Okay, because there are so many commands, there's no way that to turn all of those commands into GUI, clicks and whatnot. So understanding GDB commands here can be useful. So I'm going to run the program. So now we are in ATOF. And the nice thing about GDB is even though it is a text-based debugger, it still gives you all kinds of useful information. In other words, in this case, it tells me that the number I'm parsing is 1.023E3. Okay, it has no specific sign. Okay, so with single step, as for single step, it will go into subroutines, you know, if there's something to call. So now I'm about to call parse sign. I single step, I get into parse sign, and parse sign is given the pointer. Now inside GDB, you can always say print what pointer is pointing to, and it gives you not just saying that, oh, this is a structure. It actually gives you the individual members of that structure. So it's kind of handy because now you can actually track down, okay, I have parsed this number up to a certain point. What am I seeing here? Okay, single step, and it exited the switch statement without executing anything because the P member is pointing to something other than a plus sign or minus sign, so there's nothing to do. It goes to the default case and then it just exits the switch statement. But when I print PTR or dereference PTR again, oh, it's optimized out because we are at the end of the subroutine. Yep, I think so. That's okay. We can single step all the way back into here. Okay, it went all the way back to the beginning. So we have no way to actually check the sign is right or not, unfortunately. Okay. So it did not cause any bugs, but I can't really confirm that the program is working up to this point. So if I insert some really useless code here, that will make sure that we have a way to stop it. But I'm pretty sure this part is working, so we'll go ahead and deal with parse mantissa, which is one of the more complicated part to parse. ATOF struct, PTR. Okay, there we go. And if I want to save anything, any settings with VI that I want to use every single time, I can edit tilde/.vimrc, and in here I can insert the commands that I wanted to run all the time, such as setting the shift width to 2 so that it's not by default 8. So there we go. So now we should. Oh, okay. For some reason, it turns off the syntax. That's awesome. Okay, So now we can start with this. Oh, it actually turned off, Did I misspell something? Set shift width to 2. That should be right. Okay, getting back to here. So when I'm parsing the Mantissa, I have at least, I know there's at least one digit, right? Because that's part of the rules, part of the syntax. And we also need to parse the Mantissa itself. So there are a few things we have to do here. First of all, we have to initialize M10 to be 0, okay? Because that needs to be cleared. We also have to clear E10 to be 0. Let me see, these two are the only things that we have to do at this point. And then from here on, we are looking for digits. So we are basically saying, as long as I'm still seeing a digit, which is what PTR, the P member of the structure pointed to PTR is pointing to. So once again, if you don't have the inner parentheses, it will still work. But this just makes it more clear what we are dealing with. Okay, set AI, set shift width equals 2. Okay, there we go. Okay, so now inside the loop here, what should I do? I know that by the time I get to the cursor, P is pointing to a digit. So what do I need to do when I process a digit? There are two things we have to do. We have to do something about Mantissa, don't we? Okay, M10, we have to do some processing with that. You guys remember how we are supposed to do it? M10 gets M10 times 10. In other words, everything that we have read up to this point has to shift to the left-hand side by in base 10. Okay? Because we are just reading a new digit. So we have to make room for the new digit. So the new digit becomes the least significant digit of the number, of the value that we have read so far. Okay? So then we have to add the value of the digit that we have just read. And that would just be the dereference of the pointer minus the ASCII code of 0. So I don't have to look up the actual ASCII code of 0. And I think I gave you some code like this last time as well. Okay. And then the next thing we have to do is to remember to increment the pointer. Every single time we process something, we have to increment the pointer. And that's it. So this loop will stop if it does see the period, okay, the decimal point. By the time it gets to the decimal point, it will stop. Yep.
And what about the end of the line?
End of line?
Yeah, we need to check that.
Nope, because end of line is not a digit. It will stop as well. Yep. Right. So this is also kind of related to what I talked about last time. To stay in the loop, you only want to specify what you are expecting in order for the loop body to work. Because anything that's outside of that should get you out of the loop. Okay, so the next thing we have to do is to say we can have an optional decimal point. So anything that's optional is going to be a conditional statement. So now we can say if we see a decimal point at this point, then we'll do some more processing. Otherwise, we're done. Because if we see a D, that will automatically get out of this entire subroutine. If we see the optional period and possibly the other portion of the Mantissa, then we'll continue to do some processing. All right. So then we'll go ahead and repeat this loop here, almost, but there will be some slight changes compared to this loop here. There are 5 lines, and we need to shift it. This is also why it is nice to have a good tool that can automatically re-indent, and you can refactor and do all kinds of stuff like that, but for BI it's good enough. Okay, so the first thing we do here is to make sure that, since we have just processed the period, let's increment the pointer past the period, and then we'll just do the following. But this time, when we see additional digits to the right-hand side of the decimal point, we have to do something about E10. We have to decrease it because the decimal point is basically saying, oh, the following are fractions of the Mantissa. But since I'm keeping track of M10 as an integer and keep multiplying and stuff like that, we have to adjust E10 to take into consideration that the rest are really a fraction. So we have to say E10 minus minus, decrement E10. And that's it. That's parse Mantissa. So this would be a good time to check parse Mantissa and see whether it works. Well, we won't be able to test it unless we call it, right? So Mantissa, there we go. So now we do another make. You can see why I really do not like or have no need of a GUI, because on the command line, if I have a make file already done correctly, a simple make enter would automatically remake the entire target. Yep.
I have a question on performances and languages. So between, I guess, C and Java, like how does the, I guess, performance change as?
For exactly the same code, there's no comparison. Because, okay, so here's your i7 processor, which is the hardware, right? And then on top of this would be an operating system, like Linux or Windows or something like that. And then so when you compile a program in regular C, it is executing right here. So this is where C++ or C programs execute. It will interface with the operating system, but the program for the most part will execute on your i7 processor. It's only when you need to do file operations, then we'll ask the operating system to help it to do something. The JVM is basically an application from the perspective of Windows or Linux. So here's JVM, or the Java virtual machine, and then your Java program sits here. So the Java code, or Java bytecode, which is after it gets compiled, is actually quote-unquote executed by the Java virtual machine, which is an emulator. So it's always going to be slower. There's no way a Java program can execute as fast as a native C program that is compiled.
So in terms of, I guess, like percentage?
I do not know, because a lot depends on optimization technology and also the structure of the program. If you have heard of that term, just-in-time optimization and stuff like that, or just-in-time compilation. So what JVM does sometimes is to recognize that there is a particular loop in bytecode that is very tight, that is that executes a lot. So the JVM has some kind of what we call spot optimizer that can optimize by compiling a little bit of the bytecode into native i7 code. So that portion of the Java program executes a lot faster than the rest of the program. But that's all kind of black art. But natively, JVM is going to be slower. There should be no comparison between these two. One of the nice things about Java is it runs on any platform. I went to one of the first Java 1 conference in San Francisco. So at the time, Sun Microsystem was still around, and they held this really big convention and saying how Java is really good because it runs on every single platform. And then somebody said run, and then using a caret equally slowly on all platforms, which was true. It's just that we have super fast processor these days that it doesn't seem to be a problem anymore. All right, so we are getting back into the program, and in this particular mode, you can actually look at list ATOF from line 1. So now we are going through ATOF, the source file, and find a good spot to stop. So line 62 seems to be a good place to stop. So we say break at atof.c line 62. And then we go ahead and run the program until we hit that point, okay? So when we hit that point, it optimized the PTR already at this point. Okay, so we still have the structure. So we still have A as a structure. So there we go. The sign bit is a 0, M10 is 1023, E10 is -3. They're all correct. So when I write a program, I tend to basically run the program a lot just by testing, okay, is this code working? So I'll give it test cases. And then if you do a continue, it will continue to execute at full speed until we get to the same point again. This is for the second number. So for the second number, PTR is already optimized out, unfortunately, so we can't actually see the original string. You can't go back to the main program to see what was passed in this case. There's one particular BT is a really useful command in GDB. It's called backtrace. So backtrace allows you to find out how did we get here. So the way you read the output of backtrace is we are currently at atof.c on line 64, but how did we get here? Who called this subroutine so that we ended up here? Oh, it's main, but where in main was the call? It was on line 10 of main.c in the main subroutine. So backtrace is really helpful because just knowing that you're in a particular subroutine sometimes is not very helpful because you might have like 20 different places that you might call that subroutine. But having a backtrace gives you the idea of exactly how you got here. And not only that, you can even, you can do one thing, which is list, right? You can list main.c on line 10. So this way we can see that on line 10, we are passing this number to the subroutine. So we are expecting 1253 to be M10, and we should be expecting -4 as E10. Okay, so let's go ahead and print A and see if that is the case. Nope, I messed up somewhere.
There should still be -3.
Oh, because I haven't read the exponent yet. Right, because I haven't written parse exponent. So this is all good, okay? Because it's just reading this part at this point. The E-1 has not been parsed yet. So the program did exactly what it's supposed to. Very good. So go back to this one here, and I just can't stand this because I want to turn on AI shift width equals to 2. I think the set part may not be may not be needed. Nope, that's not what it wants. Okay. Okay, so we're back to the original thing. So now we only have one more thing to do, which is parse the exponent. Okay, so parse exponent. Same thing, pass a pointer to the structure. And it has something that's similar to the other one. So the first thing we need to do is we cannot zero out E10 anymore because E10 already has some meaningful value. So we cannot just zero it out. But one thing we should do is to see whether the pointer is pointing to a E in this case. So if it is, then we got something to process. Otherwise, we have nothing to process, nothing to do at this point. Okay. So inside here, the first thing we need to do is to increment the pointer because we have just processed one more character, and then we can see a sign again. Okay, we have to remember the sign. So now we have to say, okay, this can be a local variable. This is another trick that I personally use. Is I only declare local variables within the scope where it is needed. So I don't push all my local variables all the way to the top. I only define the local variables in the most local scope possible, okay? So it's only here that we need to do it. So the sign of the exponent, or E sign, okay? And we'll give it a default of 1, okay? This is going to be a multiplier. Okay, so the next thing we need to do is to check for the optional sign. So we now say, this is not a switch statement. If you want to use a switch statement, that's okay. But you don't have to use a switch statement because you can just check each individual case. So you can say if I see a plus sign, there's nothing to do. If I see, we have to increment the pointer. Thank you. If we see a negative sign, we got something to do. So increment the pointer first, and then over here also increment the pointer. Yep.
Could you just send it to your function to check anyways?
Send it to the function?
Oh, no, never mind.
Because that one
You got
changes the
very
sign of the
limited.
number itself.
Right.
I could have extracted that logic into another function that can be called in from both places. Okay, but in this case, we do have something to do because we have to remember E sign is now a -1 instead of the default of 1. And then after this, after the sign, we have to have numbers, okay? So now we go back into the whole loop about, while is digit, and then here we have to use dereference ptrp. As long as I'm still reading a digit, I have to do some processing. So this is also a good time to now say that, okay, we need to remember what the exponent is. So we have to remember the exponent in base 10. It is initialized to a 0. So over here, we do the same trick as what we did earlier. The first thing is to increment the pointer every single time every time we see a digit. And I want to double check, make sure the recorder is recording. Okay, it is. Well, I don't think any one of you is going to actually go back and watch the entire thing, but there might be little things that you want to pick up again. So recording it is okay. Okay. So now the next thing we have to do is to say exp10 equals exp10 times 10 plus the character that is pointed to by p.
Professor Ted?
Yep.
Wouldn't you want to increment after?
Yeah, just skip right
Oh,
past
yep.
that.
Because otherwise we're incrementing right past the character that we are supposed to process. Very good. Good catch. Okay. So now that we have just processed the exponent that is after the e, we can now multiply the sign to that thing and then use that amount to adjust E10. So now we say PTR points to E10 is adjusted by the sign of the exponent times exp10. Now what if there's no e after this thing? Well, it's okay. E10 is initialized to a 0, right? Are there any questions about this code? Well, I'm going to test it, okay? Because that's the whole point, is to test this thing as much as we possibly can. So we exit again. I'm going to see if I can change the defaults, okay? Because it really annoys me. Set AI, set shift width to 2, and then syn on for syntax on. There we go. Okay. Yep, I forgot to close one of the parentheses on line 22. Nope, that was not line 22, was it? Column 22. Okay, here we go. Column 22, and we have to do it like this. There we go. Say it one more time.
The arrow that wasn't your pointing to anything.
Oh, okay.
It was just dashed there.
There we go. T. There we go. Make, and then GDB main again. And we want to find out which line we want to stop. I always forget which line to stop, so I'm gonna list. Let me see if I can do this. Can you list? Yep, you can list a function. So we want to set a breakpoint on line 87, and then run the program and print A. Okay, it's all good. This is the first number, and then we'll. Uh-oh. Yep, because I forgot to call the subroutine. That is a good sign that you're absent-minded. You write the subroutine and then you forget to actually call that. There we go. Okay, so we want to go to ATLF, put a breakpoint on line 88, run the program, print A, okay, and it's still not getting past that E.
Did you make after you changed it?
Okay. Nope. There we go. Thank you. Okay. That's go to ATOF, for the breakpoint on line 88, run again, print A, yay, okay, that's good, okay. Continue, print A again, this is good too. Okay, so we got it. All right, so getting back. So now we have the proper structure to start to actually do the conversion. Now when we do the conversion, do you guys remember there are two distinct cases? One is when E10 is positive, the other one is when E10 is negative. Because we cannot really merge those two, because one has to multiply by 10 and then divide by 2. The other one has to divide by 10 and multiply by the other one. Yep.
In this specific homework, find an exponent. We know it's either going to be one number or it's going to be one number and bunch of zeros in front of it. So wouldn't it make sense that we just say if the number is not 0, then that's the number we're looking for.
If the number is not 0.
Yeah, so exponent can be either like 1, 2, 3, 4, or it can be 0, 0, 0, 4.
Right.
So if the number is not 0, then that's the exponent. So the last successful not 0 number is the exponent. I mean, it's more specific case, this is more general.
Right.
So, but
Yeah, this is
it should work.
this is pretty much the most general case. Yep. Okay, so we'll separate those two cases. So when a dot E10 is greater than 0, we'll handle it in a certain way. Else, if a dot E10 is less than 0, we'll handle it in another way. So the objective is to get E10 down to 0, and then we'll do the rest of the conversion. Okay, so we'll go ahead and name this subroutine E10. Okay, E10 is positive. Okay, so we'll pass the entire structure to it, and then the other one is E10 is negative. Pass the entire structure to it. So this way, I'm bundling everything into the structure, and every subroutine has the entire structure. So void E10 is positive, struct ATOF struct ATR. Okay, so this is the case when E10 is positive, which means in the loop I want to decrement E10 by 1 in each iteration. Okay, so
Question.
yep.
On is positive, don't you want to do it if it's E0 as well, or if it's...
I'm just going to do it the most general way.
Well, on the module, like the reading, the case was it was negative or not negative, not necessarily negative or positive. So would you want to take E10 is 0 into this too, or no?
When E10 is 0, I don't have anything to process. I don't need to do this part. I will still have to do the shifting later on,
That's true.
but that's all in binary already. In other words, my main objective right now is to get rid of the exponent of 10, because that's the problem, that I cannot just do bit shifting to adjust the number. Okay, so in here, without even specifying the other parts, I know when I should stay in the loop. I should stay in the loop as long as E10 of the structure is positive. Okay, and I also know that within each iteration, I should decrement E10 by 1. So this is actually how I write programs. I actually write out the outer shell of the structure first, and then I go back and fill in the details later on. So this way, it serves two purposes. I will never miss a closed curly brace, because when I open, I always close it immediately. And then the second thing is, at this time, I'm quite sure that this is what I need to do. This is the overall logic of this code. Okay? So then the next thing I do is to figure out, okay, so what else do we have to do in this loop, in this particular loop? Okay. So somewhere in here, okay, I know that we have to do because E10 is decremented, which means the amount or the division by 10 is going to be countered by M10 being multiplied by 10. Is that making any sense? Okay, so I know at some point we have to do this. But I cannot do this just yet unless I know there is enough space to do it. Does that make any sense? So this is where the check comes in handy, is do we have enough space to do it? So the way you know whether you have enough space to do it is, so we'll specify the condition first, and then we'll go ahead and deal with the, okay, we'll specify it as a loop. So once again, I specify the structure of the loop first, and to be consistent, I use one line for the open curly brace itself. And then the condition to stay in is as long as we do not have enough space, then we have to shift it by 2 and then adjust E2 accordingly. So the question now is, how do we know there's not enough space? If PTR times M10 times 10 is less than PTR points to M10, that's a sign that we are running out of space because it wrapped around. Okay? So as long as this is the case, we need to make space, and the way we make space is we will divide the number by 2. Okay, so we will say PTR M10 equals PTR M10 divided by 2, or to be faster, you can shift by 1, and then we have to adjust E2 accordingly. So this is division by 2. We have to counter the division by 2 by incrementing E2. Okay? So we have to say E2 gets incremented. But then we also have to remember that we are adjusting it. Yep?
E2 is what before?
E2 is not initialized. Okay, good point. So we have to initialize E2 first. And since we have to do it in both cases, we should do it over here. So E2 gets 0. And we also have to remember how much we have adjusted. Because E2 should be enough. So we'll just use E2 to track that. Okay? So we'll shift it by 1, and then we'll increment E2. So we'll keep doing this until there is enough room to fit another multiplication by 10. And we'll keep doing this until we don't have any exponents of 10 left. Are there any questions about this part? Yep?
Don't you have to pass E2 into the function?
E2 is a part of the structure, or if it is not, we should add it to the structure. Yeah, E2 is already a part of the structure, so we're good. All right. So we should probably test this. Okay, so let's go ahead and give it a try. Yep.
In your original main, there is no test case.
Yeah, so I have to adjust the main program to test it because these are not big enough. Okay, this one won't end up with an actual E that is positive or E10 that is positive. So we have to bump this up to, let's say, 6, right? That should test the code a little bit. It won't test the part when we run out of a 64-bit integer, but it will at least test whether it's shifting correctly. So we'll go ahead and give it a try. Okay, so make main. Let's see. It's complaining on line 109, undefined reference. Okay, because the other subroutine has not been written yet. That's okay. We'll just give it a stub for now. That doesn't do anything. Yep. Oh, there's a question. Okay, so once again, we'll test the program and we'll check ATOF again. And put a breakpoint on line 115. Run the program and print A. So it does do all the shifting correctly because you can see that it is, instead of 1,023, it is now 1,023,000, which is the correct amount. Okay, so that's good. But then I'm not satisfied with all this because I want to see whether it can deal with the case when we run out of 64-bit integer representation, because that's the whole point that I make all of those cases. So we'll go ahead and test it again with main.c, but this time we specify a much bigger number. And I think 20 should be enough because I think 16 decimal digits is the limit of a 64-bit binary number. So having E20 should kind of require some shifting to get it handled. Okay, so once again we'll make first, and then GDB main, and since I always forget which line to put a breakpoint, there we go. Okay, so print A. So E2 is only 1 in this case. Not quite sure whether that is, well, since it's 20, I think it's not right. Because E2 should be a little bit more than that. The other way you can check whether this is right or not is to look at this number, look at the mantissa, and then you just ask the question, if I multiply this by 2, am I getting the original number back? And the answer is no, we are not getting the number back. So we know it's not, that is not right. Okay, so we'll go back to the program, ATOF, and see whether we can find out why it is not working. So the way it's not working has to do with not detecting that we are running out of the range correctly. Well, there's another way to do this. The other way to do this is to figure out what is the largest number we can actually represent that before we run out. Yep.
Did you parse like the 20 for everything? Did you parse the 20 for the exponent? Because your parse exponent function might have not gotten 20.
Okay, that's a good point. Okay, so we can test that too. Okay, so we make, just to be sure, GDB main list ATOF. So we want to test it right after on line 105, just to make sure that the structure is correct. And we want to put a breakpoint on line 115 as well, which is where we put a breakpoint normally. Okay, so we will check A. E10 is 17, that is correct. So something is not right about the subroutine itself, and we know that we can only take care of about, okay, we'll use a calculator to double check. Or we can just use the math last time.
Yeah, well, since E10 is 17, shouldn't that be like around 1 for E2?
But M10 is already 1023. Yeah, so I might have made a mistake. Okay, so this is, I think I got the math wrong, because 2 to the power 64 is 2 to the power 10 to the 6, right? Plus 2 to the power of 4. So I got the math wrong, because this is about 1,000 to the power of 6. So there are 18 digits here already, and then this is 16. So the computer actually, I think the logic actually worked correctly. So I think I messed up instead of the program messing up. Because if you look at this, okay, so we can check. Okay, so we can put a breakpoint in the loop. Okay, so we say list E10 is positive, and then we can put a breakpoint on line 83, and then continue execution, and then we can, I think we can do a watch PTR, and then we continue. Okay, so this is the largest power of 10 that it can represent, and then once it gets past that point, it has to wrap around. So I think it's not dividing enough before it multiply by 10 again. So let's print A again. Because when you multiply this number by 2, it's definitely not correct. So we know the problem is somewhere here. Shifting by 1, incrementing E2. And if we keep doing that until the product of this number times 10 is less than before the multiplication by 10, until it's greater than or equal to. This is on line 83. And it has got how many digits already? 4, 8, 12, 16. Okay. So we single step. Okay, so it's ready to get out of the loop at this point to multiply by 10. So it exits the loop too early. That doesn't seem right to me. Okay, so okay. Question? Go ahead.
What were you doing before you had a max? Did a max value?
Well, I'm trying to avoid using a max value. So right now it is working. You know, we're getting back to the beginning, and it is not entering this loop. So we want to put a breakpoint on line 85 so that we do get into the loop. Okay. Okay, so we are now in the loop. So we want to print M10 before we execute the statement. Okay. And after the shifting, it should not look like 1023 blah 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 anymore because we're dividing it by 2, right? So we single step, print PTR points to M10 again, and it looks exactly the same. So the right shift by 1 bit did not work. Yep. Because M10 is already due in 64, I would think that it does not need to be casted. So, okay, so here's what you can do in GDB. You can say, you know, this thing, shift by 1, and it's supposed to be that. But it is not storing the result after the shift. So that is kind of mysterious. Okay. I'm pretty sure most of you would now, you know, actually believe me when I said, you know, I have not written this program before, right? Okay, so now the question is, you know, how do we diagnose this problem? Why is it not actually, you know, storing the result after the shift? There are 2 things I can think of. You know, one is probably not the case, which is the associativity of the operator. I do not think the shift operator has a lower priority than the assignment operator. In other words, I don't think it's actually doing this, okay? Because that would give me the result that we saw, right? But I don't think that is the case. Okay, so if that is not the case, that means we're doing this. And somebody suggested to cast this 1 because the other side is already a U in 64. So let's go ahead and cast this 1 to U in 64 underscore T so that both sides are 64-bit numbers. But that really should not be needed. Okay, so let's go ahead and This is line 85. Okay. Make BATOF.C line 85. Run the program. Okay, so this is the moment of truth. So we want to look at PTR M10. Okay, this is exactly where we are supposed to be at. Single step. And it is still the same. So somehow the right shift by one operation doesn't do what it's supposed to. Now this is mysterious to me, but if I'm really pushing for time to get the assignment done, I'm just going to use another mechanism to get this done. Because all of this is really just for dividing by 2, right? So this should do the same thing. Right? Okay, so we'll test it. So make again, gdb main, put a breakpoint on at atof.c on line 85. Run the program, print ptr M10, and it is still the same. That is very strange to me. So division by 2 doesn't work, shifting by 1 doesn't work. Well. So there is something going on here that is not doing what I wanted to do, because division by 2 is pretty clear cut what it is supposed to do, same as shifting by 1. Let me check this. Okay. I'm checking the makefile just to make sure that when I compile, I'm turning on all the warning, because warning messages can be useful, because if I'm doing something that is really stupid, the compiler sometimes will just tell me that, okay, this is not smart, do it in another way. But I didn't get any warning messages, even though I turned on the warning. Huh.
Is the loop getting executed at least once?
Well, it got to this line, but it was not actually doing anything to division by 2. And so at some point, and then it got out of the loop too, which is also mysterious, because if you can get into the loop, it should stay in the loop until the condition is false. Yep.
I had the same problem, but it wasn't, once I got out of the loop, it seemed like a loop multiplied by 10. Not some other.
Okay.
I never figured it out.
Did you cast a 10 to uin64_t? You should not need to, because M10 itself is a uin64. Yep, go ahead.
It worked before cut, but after cut, it didn't multiply by 10.
Should the operator should be greater than while it's bigger?
Well, it is greater than, okay, when the product is greater than M10 itself, that means I still have room to multiply by 10. That's how we got to 1, 0, 2, 3 followed by a whole bunch of zeros. It's only when we get to that point, then the product is now less than 1023, and then followed by a whole bunch of zeros, and that's how we get into this. Okay, so we got 5 minutes. I do want to get this particular problem fixed within 5 minutes, so I'm gonna use another approach to do this. Okay, yeah, I'm a more traditional C program. I'm going to use define here, so I'm going to use define to define max. Okay, I'll just call this max 10 here. So max 10 is going to be uint 64_t 1, and we'll shift it 63 times. Nope, actually, we want it to be a 0 minus 1. That will make it the largest possible number. And then we'll divide this number by 10. That will give us max 10. So we'll go ahead and just say that as long as this number, as long as M10 is greater than or equal to max 10, keep dividing by 2. Okay, so this is the alternative way to do this. Make again, GDB main, list ATOF. Actually, we want to list E10 is positive. Put a breakpoint on line 87 again. Run. Okay, so we got here. So we want to print PTR points to M10. Okay, this is exactly where we want it to be. Single step, print it again, and it hasn't changed. So we got to, so the loop got triggered. Okay, we got into the loop at the right point, except when we are about to do the division, it doesn't store the result. Either it doesn't store the result, or it did not compute the result correctly. I cannot quite figure out which way it is. Okay. We'll do several things. We still have about, 3 minutes left? Yep. Okay. Okay, so this will avoid any type of confusion of operator precedency and stuff like that, because I'm using a compound assignment operator to get this done. I'm also checking to make sure that the braces are not wrong. Okay, and we'll give it one more try. Okay, print. Okay, we can also do a watch. Okay, so watch is actually kind of cool, because when you do a watch, every time the value is changed, it will tell you how it's changed. So we single step, and it did not trigger the watch, which means the value has not changed. Okay, I am stumped. I am a little bit stumped here because the division is not working. Okay, what do you think is going to be the next step? We won't have enough time during the lecture, but I will continue this over at the lab. What happens when the compiler doesn't seem to be doing what it is supposed to do? You question the compiler. How do you question the compiler? Get a new one. No. Okay, so what you do is you look at the code that is actually generated, look into the assembly code and see whether it looks right or not, which is part of the reason why you want to take a class like this, is when the tool doesn't work correctly, you want to have a way to kind of go like, okay, why is it not working correctly when it is supposed to? Okay. So I'm gonna call this the end of the lecture, but I will continue to work on this, in the lab, and you don't have any homework assignments at this point. So you have a short break. Yep.
Does this mean we'll have more time for this homework?
It depends on whether this is a problem that you're getting into.
Similar, yeah. I'm stuck, right?
You're stuck with something like that? Okay. All right, so we'll go ahead and call this the end of the lecture, but I will think about that, okay? Depending on, if this compiler is doing this, it is likely that the Windows version is doing the same thing, because this has nothing to do with the operating system. It is actually the compiler itself. Okay, alrighty, so I'll see you guys probably on Thursday.